Hi and Assalamualaikum to all respectful panels and audience. My name is Nur Aina Adrina binti Muhammad Shukri from Faculty of Mechanical and Automotive Engineering Technology, University Malaysia Pahang. The title for my study is Surface Strain Measurement on Pressurized Stick Wall Pipe by Fiber Bragg Grating Sensor and Strain Gauge. Pipes and pressure vessels have been broadly utilized for decades and becoming a source of importance in engineering technology as a medium to convey and store high-temperature liquid and gases. So they have a multitude of applications in industry, including power plants or refineries, submarine technology, aircraft fuselage, as well as gas reservoir. In the last decade, the popularity of optical fiber for real-time structural monitoring has expanded significantly. Optical fiber sensors, such as fiber Bragg grating sensor, dominating the engineering field as the most promising sensing technology, with its great feature for multiplexing capability, lightweight, immune to EMI and RFI field, thus applicable in harsh conditions. Corrosion and stress in the pipeline are two major contributions to the leakage accident in the pipeline industry, and thus monitoring this parameter had become an important research topic. A pipeline is considered to be a pressure vessel with comparatively stable inner pressure during a long-term service operation. Thus, the indirect leaking monitoring method can be designed by measuring the effect of changes in internal pressure. With an increase of internal pressure, the circumferential and longitudinal strain can be measured on the outer surface of the pipeline. So the objective of this study are to measure the surface strain on the pipe vessel based on the internal pressure impact, and also to evaluate the behavior of FDG and conventional resistant foil strain gauge sensor. The theoretical calculation of longitudinal and circumferential strain induced in the carbon steel pipe were calculated by using two-step process. The stress acting upon the principal axis is determined by using the formula of limb theory as shown below as in the first equation. And then from the stress calculation, the strain output can be calculated in the next step by using this formula, which is the second formula. The strain sensitivity of directly at higher FPG sensor is 1.2 pm per microstrain under a constant room temperature at 27.5 degree. The relationship between the changes of the central wavelength of the FPG and the strain can be expressed as the following equation. The FPG sensor used is an acrylic-coated single-mode fiber which made of silica glass, having a diameter of 10 micrometer and its clad diameter of 125 micrometer. Two FPG sensors with a wavelength of 1550 nanometer and 1556 nanometer were adopted by multiplied these two sensors into a single line optical fiber to measure the longitudinal and circumferential strain respectively. In this experiment, as shown in figure 1, so the pipe is connected to test pump by a hose. The hydro test pump will generate a pressure inside the pipe vessel by pumping the water from the water bath tank into the pipe. Figure 2 shows the FPG and RFSG sensor are bonded on the surface of the pipe in an orthogonal geometry on the principal axis of the pipeline by using a cyanoacrylic glue. Meanwhile, in figure 3 shows the schematic illustration of the experimental layout for FPG demodulation instrument. SLD light source is connected to FPG sensor by using a circulator. So the back reflected spectrum from the FPG sensor was captured by OSA and monitored by using a PC or computer. In this experiment, the pipe was internally pressurized by using the tap water and performed under a series of pressure ranging from 0 to 5 megapascal with a maintained temperature under control room temperature and 27.5 degrees Celsius. The internal pressure is increases with a step of 1 megapascal and maintained for at least 3 minutes in each step. So the wavelength shift of the FPG sensor is recorded from 1 to 3 minutes for each step to reach its stable condition. The test process is then repeated for 3 times with loading and unloading step in order to analyze the resilience and repeatability of both sensors. So figure 5 showing the recorded data of longitudinal surface strain comparing both sensors between FBG and RFSG sensor. The longitudinal strain measurement data, as shown in figure 5, portray a good reasonable agreement between both sensors. The strain response is initially proportional to the pressure. Throughout the test, it can be seen that the strain response of the FBG sensor does not vary and possesses good stability and repeatability during loading and unloading period. The stability of the output signal is a main feature to validate the robustness of this sensor for SHM system. However, the pattern of RFSG as shown in figure 5b are not truly consistent within the 3 replication trial, and a high hysteresis response is observed which is not detected by the FBG sensor. So the RFSG sensor generates much noise compared to the FBG sensor that significantly influence the data precision of the RFSG sensor, especially when the strains are relatively small. Meanwhile, the strain response in circumferential direction was recorded and plotted in figure 6 when the pressure is increased and decreased for loading and unloading period. It can be clearly seen that circumferential strain possesses the same trend with a longitudinal strain, which showing the FBG sensor possesses higher repeatability and stability output compared to RFSG sensor. The instrument repeatability error for both sensors were calculated and summarized in table 1. So from the table, FBG sensor possesses lower repeatability error with a percentage of 1.08% and 6.17% for longitudinal strain during loading and unloading period respectively. Meanwhile, for FBG circumferential strain, the percentage were recorded at 0.75 and 2.08 repeatability errors during loading and unloading condition. The lower repeatability error indicated that the FBG sensor were constant in data measurement throughout the test. However, higher repeatability errors in longitudinal and circumferential strain value were recorded by RFSG sensor, with a percentage error of 17.91% and 3.34% for loading condition and 35.07% and 18.25% for unloading condition respectively. So such discrepancy and data measurement could be suspected that RFSG sensor was suffering due to hysteresis error. Next, the comparison of both surface strain was done by plotting the average value for longitudinal and circumferential strain versus pressure, as can be seen in figure 7. The previous equation were used to provide a theoretical prediction of the strain value. So in this figure 7, the error in the data measurement are clearly noticeable between both sensors with a theoretical prediction. From figure 7a, FBG sensor had higher linearity compared with RFSG sensor with R square equal to 0.9988. On figure 7b, the linearity of FBG sensor is R square equal to 0.9611, which much lower than RFSG sensor. So it can be concluded that in terms of linearity, FBG sensor exhibit an excellent linearity at longitudinal strain with 0.12%, while RFSG sensor exhibit much lower at circumferential strain with 0.03%. However, the RFSG sensor suffer a systematic error. So it can clearly observe that the reading in both sensors was slightly above the theoretical value. So this distinction in reading might be due to slight deviation in the angle alignment, or also might be due to inconsistency in surface finishing in the pipe thickness due to internal defect. However, since both FBG sensors are much closer to theoretical prediction value and possess higher stability output, it can be argued that FBG sensors are more accurate. It can be concluded that FVG sensor possesses a better stability and repeatability data output with a lower percentage error when compared to RFSG sensor. In terms of linearity, FVG sensor have the appearance of being more stable with a percentage error 0.12% in longitudinal strain and 3.89% in circumferential strain measurement. Therefore, it is clear that FVG sensors are more reliable in real-time monitoring and detecting the pressure variance in a pipeline. That's all for my presentation. Thank you.